The purpose of this video is to demonstrate a method for evaluating trig functions algebraically. This method is useful when we want to show how some functions relate to other functions, and trigonometric identities. When we want to evaluate kind of the mechanics, algebraic mechanics behind the derivative of trig functions, and most useful is also how it pertains to the integral of trigonometric functions, tangents and secants, and I'm going to show that at the end of the video. But to start off, let me just get right into it. So this is going to be a unit circle. I'll write that over here. This is a unit circle such that g squared plus h squared is equal to 1, gh being a coordinate on our circle. Then we have this line here, L. So L is going to be a line through -1, 0. And our goal is going to be to express our point along the unit circle, gh, in terms of a parameter t. So I'm going to write that goal here. We want to express g and h as functions of some parameter t. And L is going to be the line through the point -1, 0 and the point g of h, gh, which is a point on our unit circle, such that g squared plus h squared is 1. And I want to just point out that for each point on our circle, we have a unique line L, meaning that line L has a different slope. Which is important because that slope is going to be the parameter t that we use to parameterize this circle. So if I can find a value, if I can find g and h in terms of t, the slope of L, so I'll write that here, t is the slope of L. Then I'll have a function from the so the domain of that function, gh, or the functions g and h. So if I can get g and h as functions of this parameter t, and the parameter t is the slope of the line L, then I can determine a formula that I can plug t values into that will give me points along the arc of the circle. So this method is, I think, called the method of Diophantus. But it's extremely useful, and I'm going to get into that before the end of this video. Extremely useful when we want to uncover the mechanics, algebraic mechanics behind integrating and differentiating these trig functions. That's, I think, the most useful aspect of this method, but also you can use it to verify trigonometric identities and things like that. So real quickly, we know what the slope of t is. T is going to be equal to h divided by g plus 1, which means that h has this relation t times g plus 1. Alright, so now I have h in terms of t and g, and then I have g squared plus h squared is equal to 1, this relation that gives us the circle. So if I plug in this formula for h into that equation there, it should give me 2 points. So that's the intersection of a line and a circle. This comes from our line L, and this comes from the circle. And the two values it will give me will be 1 here, the point that we're interested in, and then the other value should be, it'll give me -1. G is equal to -1. So I'm going to write that here, g squared plus h squared, which is t times g plus 1 squared is equal to 1. Okay, and then the goal is to solve for g. And once we I've actually already done that a couple of times in the first take of this video. And I'm not going to work it out because in the interest of time, I don't want this video to be too large that I can't upload it or do anything with it. So I've went ahead and solved that quadratic equation. So here we have what I just wrote, g squared plus t times g plus 1 squared is equal to 1. And then we have a quadratic equation in g. So I can isolate our g squared term here, and then we have that multiplied by some other t term here, and then we have a single g to the first power here, multiplied by another t term, and then plus this term there. So we can either use the quadratic formula on this equation, or we can solve it by completing the square. I just completed the square to show all the steps. And that gives us g is equal to -1. That point, the intersection point of the circle and -1, 0. And it also gives us the other point, g is equal to 1 minus t squared divided by 1 plus t squared. So that is the point that I was interested in here, that g value. So I'm going to rewrite that over here. So once we solve it, we get g is equal to -1, which gives us that point. And we also have g is equal to 1 minus t squared divided by 1 plus t squared. And then I can plug that into my h equation here. T times 1 minus t squared divided by 1 plus t squared plus 1. So this is 1 minus t squared plus 1 plus t squared divided by 1 plus t squared. T squared minus t squared, and I'm left with 2t divided by, once I multiply the t in, so I'm left with 2 in the numerator, and multiply the t in there, and I get 2t, and 1 plus t squared. Alright, so now this is h and g. Alright, and another thing to note is that g is the cosine of theta, theta being that degree value or arc value. And then we have h is the sine of theta. Or in other words, cosine theta, it can be expressed by this parametric equation, 1 minus t squared divided by 1 plus t squared. And sine of theta can be expressed as 2t divided by 1 plus t squared. T being the slope of the line L. And I guess I can go ahead and put this in right now. I'll explain this in just a moment, but this is actually theta divided by 2. And if we see this large triangle here, then we can see that the slope t is also, so t can also be expressed as the tangent of theta divided by 2. Since the tangent relationship of right triangles is the opposite side over the adjacent side, the opposite side being g, the adjacent side being h plus 1. I'm sorry, h divided by g plus 1, which is t here. Got that backwards. Which is also the sine theta divided by cosine theta plus 1. Sine theta divided by cosine theta plus 1 is h divided by g plus 1, which is the slope of the line L. So these are all the same. And this is actually, this part, tangent of theta divided by 2 is equal to sine theta divided by cosine theta plus 1. That's another trigonometric identity, a half-angle formula. It arises from, well, I'll explain that in a moment when I get into differentiating trig functions. So this is the kind of the intro of what this video is going to be about. Parameterizing points along the unit circle. Points along the unit circle, it corresponds to our trig functions. That's what trig functions are. Okay. Alright, so just a quick reminder, we know cosine theta is 1 minus t squared divided by 1 plus t squared. Sine theta is 2t divided by 1 plus t squared. And so I was saying that we can use this to verify certain trig identities that we already know. So we know this is true. Sine theta squared plus cosine theta, that just follows from the definition. Sine theta squared plus cosine theta squared is equal to 1. But another Pythagorean identity that we also know is tangent squared theta. Well, we know if we've studied trigonometry, this is one of the things that, one of the Pythagorean identities that arise. I'll just show that really quickly. So this is a unit circle with all of the different line segments here representing a different trig function. So in the unit circle, if this is theta, then the tangent of theta is going to be that line segment, the length of that line segment, and the secant of theta will be the length of that line segment, and then that's the radius, so that's 1. This is a right triangle here because that's a tangent line, so it forms a right triangle with the radius of the circle. So from there, that's how the Pythagorean identities arise, from looking at the different similar right triangles here and just seeing how they how the Pythagorean identities relate to each other using the Pythagorean theorem, which is in a right triangle, a squared plus b squared is c squared. So in this case, it would be tangent squared plus 1 squared is equal to secant squared, or what I wrote here. Alright, so it should be possible, it's easier to see it geometrically, but it should also be possible if we plug in our parametric formulas for our trig functions here and solve it. We should be able to verify it that way. So tangent theta, I'm just going to write what tangent theta should be. We know tangent is sine divided by cosine, so they have the same denominator here. So if I divide this rational function by this rational function in t, then I should get the numerator divided by the numerator. The numerator of sine divided by the numerator of cosine, since they have the same denominator. So that will end up being 2t divided by 1 minus t squared. And similarly, secant of theta, I should be able to figure out what the rational function is for secant of theta just by looking at cosine. So secant is the multiplicative inverse of cosine, or the reciprocal rather. So that's going to be 1 plus t squared divided by 1 minus t squared. Just flip the numerator and the denominator. Okay. So I can take these two functions here, plug them into my formula, my equation, and I should be able to verify that this is true. So let's do that. 2t divided by 1 minus t squared. This is going to be squared plus 1 is equal to secant squared, or 1 plus t squared divided by 1 minus t squared squared. So here we have 4t squared divided by 1 minus t squared squared plus, I'll just rewrite 1 as 1 minus t squared squared divided by 1 minus t squared squared. And then I just want to transform this side into something that looks like that side to verify that this is true. So this is going to end up being 4t squared plus 1 minus 2t squared plus t to the fourth. So these have the same denominator. I can just combine them like that. I just square this term out and then add it to the 4t squared, and I end up with, sorry, this is the denominator. And I'll end up with 1. 4t squared minus 2t squared is plus 2t squared plus t to the fourth. Okay, and then we can see that the two sides match up. So we verified that our parametric equations satisfy this equation, or this formula that we know is true. This is also useful not just in verifying what we already know is true, but we can also solve more complicated trig identities as well. And so it's easier to see the geometric proof of this rather than this algebraic example. But this one here, 1 plus cosecant theta is equal to cosine theta times cotangent theta divided by 1 minus sine theta. This one's a little bit more complicated to show geometrically, but if we use our parametric formulas, we can just reduce it to more simple algebra. So this is going to be 1 plus t squared divided by 2t is equal to. So I'll write cosine of theta times cotangent of theta. First, cosine is 1 minus t squared divided by 1 plus t squared times the cotangent is the reciprocal of tangent, so 1 minus t squared divided by 2t. And then I'll multiply that by 1 divided by 1 minus sine theta, or 1 minus 2t divided by 1 plus t squared. Alright, so the goal now is to just simplify this and show that each side of this equation matches up. So we have 1 plus 2t plus t squared on the left hand side divided by 2t, which is just 1 plus t squared divided by 2t. On the right hand side we have 1 minus t times 1 plus t times 1 minus t times 1 plus t divided by 1 plus t squared times 2t, and then I have 1 divided by 1 minus 2t plus. Sorry, I'm not going to explain every step because I don't want to get bogged down in the algebra. So we'll just notice that this will cancel with that. This actually factors to be 1 minus t times 1 minus t, so I can just divide those out, and then we're left with 1 plus t squared divided by 2t. Alright, so if you just saw what I did here, you'd see that these two sides do match up, and we verified this trig identity using the parametric formulas. And this is, I suppose it's possible to do it geometrically as well, but I'm not entirely sure. Alright, okay, so the next step is to talk about how these are useful in calculus and understanding calculus. So the first part of the video just required mainly knowledge of algebra and trigonometry, but this part of the video is also going to require knowledge of calculus. Okay, so I'm just going to redraw the picture I had earlier. So this point is cosine theta, sine theta. and that's going to be our theta. This is the line connecting negative 1, 0 to the point on the circle. And then here we have theta divided by 2. I think I mentioned that. So there's a geometric proof here that we could apply to this to see that this is theta divided by 2. I'll just say what it is really quickly rather than write it out. So we know that these are interior. So if this is an alternate exterior angle to this triangle, we know that the two interior angles here and here will add up to be the alternate exterior angle there. That's a proof in geometry. The reason for that being is that there's 180 degrees in a line, 180 degrees in a triangle, and then this angle is common between those two. So the sum of these three angles and the sum of these two, if we subtracted out that common angle, we would be left with this is equal to those two. And then also, since this is an isosceles triangle, meaning this radii here is equal to that radii, that the two angles should be equivalent as well. So it's just exactly theta divided by 2, each of those angles. So that was important in noticing that, well, our t, the slope, the parameter we use to define each of these points along the circle, is equal to the tangent of theta divided by 2, or that angle there. In other words, the slope was the slope of that line was the height divided by the change in y divided by the change in x, or sine of theta divided by cosine theta plus 1. And I'll go ahead and write that again. Sine theta divided by cosine theta plus 1. And I guess I'll go ahead and write what sine and cosine is as well. So we know cosine theta, the parametric equation was 1 minus t squared divided by 1 plus t squared. And similarly for sine, it was 2t divided by 1 plus t squared. So an exercise that might be really useful to just kind of prove it to yourself is go through and take different values of t. In other words, different slopes of the line. So for instance, if you took 1/2, it would be a slope like there, and then you'd get a point here. So if you plug in 1/2 into these equations, you should get a point on the circle, which satisfies sine squared plus cosine squared equals 1. If you were to take a really large number, like 10 or something, your slope would be steeper, and you'd end up with a point along over here. Similarly, with negative 10, you'd end up with a point along there. And if you plugged in 0, of course, the cosine of theta at t is equal to 0 is going to be 1 divided by 1. It's going to be 1. And sine will be 0 divided by 1, which is 0. So just kind of as like to show yourself that slope actually does parameterize the unit circle. So what I want to show here now is that I want to see theta, a function of theta in terms of t. Well, if I want to do that, I can take this fact here, that t is equal to the tangent of theta divided by 2, and I can write theta is equal to 2 times the inverse tangent of t. So now I have theta as a function of t, and the thing to note here is that these functions change at different rates. The parametric function, and then if I were to take theta to be, have a constant rate of change, then we would notice that the parametric equations don't have the same rate of change. So that's important to note. So a prerequisite here, we're going to need to know how to differentiate the inverse tangent function. So I'm just going to write this over on the side, and I can show this as well in another video. I don't want to get into it and get off topic, but let's say I have some function y, which is a function of x, and I want to take the derivative of the arctangent of that function y with respect to x. Then that's going to be 1 divided by 1 plus y squared times dy dx. And like I said, I'll make more videos on this topic later, its application, so that we can better understand it. But the purpose of this video is just to describe this method of evaluating these trig functions with these parametric formulas. So I'm just going to use this fact here, and I'm going to take the derivative of theta with respect to t. So d theta dt should be equal to 2 dt. Whoops. I'm sorry. It's equal to 2 times 1 plus t squared. And so this kind of requires some knowledge of calculus as well, like the fundamental theorems of calculus and how this notation makes sense. But I'll get more into that later as well. Another way to write this would be d theta is equal to 2 times dt divided by 1 plus t squared. But I'm going to use this form for this page right here. And then the next page I'm going to use this form. And so if I want to take, let's say I had our sine theta was, actually, I'm going to write it over here. So I know sine theta is equal to 2t divided by 1 plus t squared. And if I want to take the derivative with respect to t of each side of this equation, a little bit squished, then I want to verify that I can do this operation and it will make sense. So I know the derivative with respect to t of sine theta is going to be cosine theta times d theta dt, and that should be equal to whatever the derivative of this is on this side. So I'm going to have to use the quotient rule to evaluate this rational, to take the derivative of this rational function here. It's going to be 1 plus t squared times 2 minus 2t times 2t divided by 1 plus t squared squared. Okay, so just a reminder, cosine of theta was this. So what I want to show for this side of the equation is that it's this function times this function, or cosine theta times d theta dt. And so that's 2 plus 2 t squared minus 4 t squared divided by 1 plus t squared squared. And this is 2 times 1 minus t squared divided by 1 plus t squared. Okay, perfect. So now I can see that this is just 2 divided by 1 plus t squared times 1 minus t squared divided by 1 plus t squared. So if I just see it like that, I have cosine theta times d theta dt, which is what I wanted to verify. So differentiating sine makes sense, and if I differentiated cosine similarly, it would also, I should be able to show that it matches up like that as well. Alright, so now this is one of the more useful aspects of this method, I think, is we can use it to integrate functions like tangent of theta, d theta. So just a reminder, tangent theta is sine divided by cosine, or 2t divided by 1 minus t squared. And d theta, if you remember what I wrote on the last page, is 2 dt divided by 1 plus t squared. Okay, and then another thing we're going to need to know, and I'll make a video on this as well, because this is a topic that shows up over and over again. But if you're studying calculus, you know this. You know this fact that if I have some function u and I take the integral of du over u, then that will be the natural log of the absolute value of u plus a constant. So we're going to use this fact as well. Alright, so I have the integral of tangent theta d theta. Let me just use my parametric equations here and substitute them in. So that's 2t divided by 1 minus t squared times 2 dt divided by 1 plus t squared. So there are other ways to show that the integral of tangent theta d theta is the natural log of secant theta, but this is, I guess it's another way. It's a straightforward way, I think, in my opinion. I mean, there are probably more straightforward ways to show this integral, but this is one of them. So let me just go ahead and show it. So that's going to be 4t. So this is going to be the integral of this rational function. So we're reducing these trig functions into integrals of rational functions, which are easier for us to evaluate. Alright, so here it requires an algebraic technique of decomposing this rational function into two separate ones. I'm not going to show all that. I'm just going to skip ahead a little bit here and just write what it is. So I can see this as being two separate integrals. I can distribute the integral in. So I guess I could write that 2t dt. I'll write that there. Write the integral there. Sorry, it's a little cramped. I could have written that better, but okay. So now we want to notice that we're going to use our integral here. Now I have, if this is 1 minus t squared is u, then I'm going to end up with, I can have a negative here and a negative on the inside of the integral, and see that that will be du of the bottom, of this bottom term. If I were to differentiate it, I would get the du term on top. So I'll just go ahead and skip over that a little bit and just write it out. 1 minus t squared plus the natural log of 1 plus t squared plus constant. So in future videos I'll talk more about how this is derived as well. I find that interesting. I know I'm kind of skipping a full in-depth explanation here, but this integral, at this point it's just going to be properties of logarithms. If I have this logarithm and I subtract this logarithm from it, I can rewrite this as the natural logarithm of 1 plus t squared divided by 1 minus t squared plus c, which, if we recognize this, is actually the, so now this is, on the inside here, is going to be the secant of theta, because secant theta was the reciprocal of cosine, which was 1 minus t squared, but this is going to be 1 plus t squared divided by 1 minus t squared. So I can rewrite it now as the natural log of secant theta plus constant. Alright, so that was our goal here. We wanted to show if we could find out what the integral of tangent theta d theta was. And in many calculus textbooks they'll give you the formula here. I And I know there's another explanation that involves an explanation of the natural log function and how it works. There are other explanations to this, but this is kind of the mechanics behind the algebra that I find it really useful. And so, lastly, I think I want to show the integral of secant theta d theta as well. So just a reminder, our secant theta was equal to 1 plus t squared divided by 1 minus t squared. D theta was 2 dt divided by 1 plus t squared. And also, I'll just rewrite this as well. Alright. And I guess we're going to need this fact as well, so I'll go ahead and write this. Tangent of theta is equal to 2t divided by 1 plus t squared. Alright, so automatically we can see we can divide out a 1 plus t squared term here, and we're left with the integral of 2 dt divided by 1 minus t squared. Then we can factor that bottom term, and we have the integral of 2 dt divided by 1 plus t times 1 minus t. And this is actually very similar to the last one. Which is actually interesting, is that we reduce these problems into similar problems of integrating rational functions. So actually, I think this is, it was very enlightening for me when I'm trying to learn about trig functions, to know that we can just reduce these trig functions to rational functions of this parameter t, and then we know how to integrate rational functions. So what was I saying? Alright, so I'm just going to go ahead and decompose this into, this is going to be the integral of 1 over 1 plus t, dt over 1 plus t, plus the integral of dt over 1 minus t, and then this ends up being the natural log of 1 plus t, plus the natural log of 1 minus t, plus a constant. And then properties of logarithms, that's 1 plus t divided by 1 minus t, plus constant. And then I'm going to rewrite my natural log function here as 1 plus t times 1 plus t divided by 1 minus t times 1 plus t. And when I multiply this out, let's see how much room I have left to work with. I have 1 plus 2t plus t squared divided by 1 minus t squared plus c. And then I have, let's see, I'm going to rewrite it over here. Natural log of 1 plus t squared divided by 1 minus t squared plus 2t divided by 1 minus t squared plus constant. So I just separated this this rational function out into those two rational functions. And then I can see that this is our secant function, and this is, wait a minute, that's supposed to be a negative. And this is our tangent function. So this ends up being natural log of secant theta plus tangent theta plus constant. So using this method of rational functions, we can show these how these trig identities work, how we integrate one trig function and we get a natural log of two other trig functions, and you can actually do this with many more complicated expressions, and I'm going to do more videos on that in the future. Thank you.